Spring 1939. Aberdeen Proving Ground, Maryland. American tank engines crawled along at 12 miles per hour, barely faster than a man jogging. Across the Atlantic, German panzers tore through Poland at 25 miles per hour, driven by purpose-built engines refined over years of research. Colonel William Christie sat at his desk, studying intelligence photos spread before him. America had just 400 tanks. Germany was building more than that every month. War was approaching fast, and the United States had perhaps 18 months to match what had taken Germany a decade to achieve. Then Christie's eyes caught something in the corner of his office, a technical manual for the Wright R975 Whirlwind, a 9-cylinder radial aircraft engine capable of 400 horsepower. It was already in mass production. His engineers thought the idea was madness. Aircraft engines operated at 2,400 revolutions per minute, cooled by rushing propeller air at high altitudes. Tanks slogged through mud and dust with no airflow at all. The vibration alone could destroy a chassis. Every textbook said it was impossible, but Christie saw what others didn't. While German engineers had spent years designing the perfect tank engine, America had inadvertently built one and called it an A-plane motor. The question wasn't if it could work. It was whether anyone had the courage to prove it. On a gray October morning in 1939, Christie walked into Continental Motors headquarters carrying a leather briefcase that contained America's most urgent military secret. Inside were reconnaissance photos from Poland, German panzer divisions advancing across conquered land at speeds no American tank could match. Even more alarming were production reports showing Nazi factories turning out tanks at a rate that would leave the U.S. defenseless within 18 months. The air inside Continental conference room smelled of oil and cigarette smoke as Christie spread the photos across the polished table. Around him sat Detroit's finest automotive engineers, men who had spent their careers perfecting car and truck engines. They studied the photos in silence until Christie spoke. America needed thousands of tank engines, fast. "Gentlemen," he said, opening a second folder, "I want to show you something that might sound impossible." He revealed technical drawings of the Wright R975 Whirlwind, a compact 400-horsepower radial engine weighing only 650 pounds and already being built nearby. Chief Engineer Robert McNamara examined the document skeptically. The Whirlwind, he argued, was meant for aircraft. Its high RPMs, gyroscopic forces, and reliance on airflow for cooling made it wholly unsuited for tanks. "Colonel," McNamara said, tapping his pencil on the specs, "aircraft engines and tank engines solve different problems. The vibrations alone would shake a tank to pieces. It can't be cooled properly." Christie was ready for the objection. From another envelope, he pulled out intelligence gathered by British agents on German engines. "The Wehrmacht's tanks," he explained, required synthetic lubricants, precise machining, and frequent overhauls, every 150 hours of operation. They took years to develop and depended on industrial conditions America didn't yet have. "We don't have 3 years," Christie said quietly. "We have 18 months, maybe less. If we can't design an engine, we must adapt one." The room went silent. McNamara turned toward the factory floor below, an ocean of moving assembly lines inspired by Henry Ford. Then an idea struck him. "Maybe we're asking the wrong question," he said slowly. "Instead of wondering whether an aircraft engine can power a tank, we should ask how to make one do it." Over the next weeks, Continental's engineers tore apart the R975's design. What looked like weaknesses turned out to be advantages. The radial layout allowed better air circulation, larger cooling fins, and a forced air fan could compensate for ground conditions. Reinforced mounts and rubber pads could dampen vibration. By November 1939, they had blueprints ready. The modified R975 would soon roar to life, the heart of America's first modern tank force. It would require a 24-inch cooling fan mounted directly to the crankshaft, custom-engineered mounts to absorb vibration, and modified fuel and electrical systems optimized for ground operation. The projected output remained 400 horsepower, 60% greater than any American tank engine then in service. The first prototype arrived at Aberdeen Proving Ground on a cold December morning, exactly 2 years before Pearl Harbor would make Christie's warnings prophetic. The modified R975C1 had been fitted into an experimental M2 medium tank, its broad 45-inch radial engine necessitating a redesigned rear hull. Test engineer Captain James Mitchell climbed into the driver's seat with tempered skepticism. His prior encounters with U.S. tank engines had been plagued by overheating, breakdowns, and loss of power that left vehicles immobilized during exercises. The radial aircraft engine started with a deep, resonant growl unlike anything he had heard before. For 6 straight hours, the M2 tore across mud, sand, and inclines without a single failure. Mitchell recorded every reading: oil pressure, vibration, temperature. The cooling fan kept the cylinders well within limits even under heavy throttle. Reinforced mounts neutralized the gyroscopic torque that had once been feared destructive. Most surprising of all, the aircraft engine burned less fuel. The R975 C1 delivered 2.5 miles per gallon against 1.8 for its competitors. That fractional gain would later prove decisive in long campaigns where fuel lines dictated victory. By January 1940, Aberdeen's test confirmed Christie's conviction. The Wright R975 Whirlwind, adapted for ground service, surpassed every American tank engine in output, endurance, and efficiency. The challenge now shifted from feasibility to production, scaling output faster than any American factory had ever attempted, as Europe dissolved into war. By spring 1940, Continental Motors' Detroit plant had transformed into a wartime laboratory. Chief Engineer Robert McNamara faced a crowded room of exhausted machinists, draftsmen, and supervisors working 16-hour days. On the blackboard behind him were chalk sketches of cooling ducts and mount brackets. The immediate crisis was airflow. Aircraft engines relied on 200-mile-per-hour wind for cooling, an impossibility inside a sealed tank hull. McNamara's team studied Detroit's industrial ventilation systems and devised an ingenious fix: a 24-inch fan directly linked to the crankshaft, enclosed in a fabricated aluminum shroud channeling air across every cylinder fin. The fan absorbed 15 horsepower, reducing net output from 415 to 400, but sustained full power without overheating. Production foreman Frank Martinez supervised fabrication of the first shrouds, hand-shaped aluminum ducts later mass-produced by stamping presses. Vibration was the next adversary. Aircraft installations dispersed the radial engine's rotational forces through propeller assembly, but tanks offered no such outlet. The 9 firing cylinders created intense torque that could crack casings and shear shafts. Working with Chrysler's M3 tank team, engineers designed new rubber-isolated engine mounts with 4 to 7 connection points, each calibrated to specific load tolerances. Testing proved the mounts absorbed vibration without structural compromise. Then came an unexpected revelation. The radial layout itself distributed heat and stress evenly around its circular form. Inline engines focus energy along a single axis, but the R975 geometry spread it across 9 cylinders, preventing the catastrophic failures that had haunted early designs. What had once been an A-plane safeguard became the U.S. Army's mechanical advantage. Reliability in ground vehicles meant survival. An engine failure could doom both crew and mission. The maintenance problem was just as severe, but led to innovations that reshaped military vehicle design for decades. Aircraft engines were serviced in heated hangars with cranes and specialized tools. Tank engines demanded repairs in muddy fields under fire. Continental's engineers redesigned access hatches, relocated oil filters for easier reach, and standardized bolts to match the tools soldiers already carried. By June 1940, the Continental R975 C1 had completed durability trials that exceeded every established benchmark. It maintained a steady 400 horsepower over 200 test cycles, with fuel economy averaging 2.5 miles per gallon versus 1.8 for rival engines, a gain that would determine operational range in battle. The urgency skyrocketed after France fell that same month, leaving Britain alone against Nazi Germany. U.S. military orders surged from hundreds of thousands of tanks as commanders realized industrial speed would decide the war. Continental now faced a staggering task: mass-producing a modified aircraft engine while Wright Aeronautical still needed the original R975 for airplanes. The solution required a complete rebuild of Continental's production system. Factory manager Sarah Williams oversaw installation of new radial engine assembly lines inspired by Detroit's car industry. Auto mechanics accustomed to inline engines learned to assemble 9-cylinder radials with jigs and fixtures born of relentless experimentation. Quality control became sacred. Each R975C1 went through 47 inspections, from crankshaft balancing to cylinder tolerances measured to 1,000th of an inch. Test cells ran day and night, pushing finished engines through full-power combat simulations. Any engine that failed was torn down piece by piece, its flaws studied before another soldier's life could depend on it. By September 1940, Continental's monthly output exceeded 800 tank engines, triple the rate of Wright's aircraft production. This wasn't just mechanical adaptation. It was proof of what American industry could achieve under existential pressure. Workers took pride in knowing their engines would soon power tanks across oceans into battles unseen. That validation arrived from North Africa. British field reports on Lend-Lease Sherman tanks revealed an 80% operational rate in desert warfare, far above the 60% German average, hampered by part shortages and breakdowns. The gamble on aircraft engines had paid off, but the true test was yet to come. Pearl Harbor would soon make Christie's predictions tragically accurate, forcing the U.S. into a total war of machines. In its wake, Continental Motors became the beating heart of the tank program. By February 1942, military planners faced an impossible demand: deliver thousands of tanks to multiple fronts while German U-boats ravaged supply convoys. The M4 Sherman offered the answer, a tank built around the R975 itself. Its wide rear hull perfectly fit the 45-inch radial, and its philosophy mirrored America's industrial logic: build fast, make it reliable, and keep it simple. Sloped armor provided protection without excess weight, ensuring mobility and ease of production. Most importantly, the Sherman's engine bay had been designed from the start for Continental's power plant, eliminating the costly retrofits that had haunted earlier models. Continental's Detroit facility erupted into relentless motion. Sarah Williams once again led the charge, organizing triple-shift operations that kept the plant running without pause. Ordinary factory workers, many new to military production, learned precision assembly at a pace no one thought possible. The process demanded 8 to 7 separate operations, from machining the crankcase to final inspection, and forged the mechanical heartbeat of the Sherman, the tank that would carry democracy across a burning world. Testing was performed by specialists executing each task within precisely timed intervals. The data itself told the story of America's wartime mobilization better than any speech or policy paper. In 1942 alone, Continental produced 8,000 R975 engines, more than Germany's total tank output for the same year. By 1943, production reached 21,000 engines a month, tripling Wright Aeronautical's aircraft rate. Though based on the same design, the scale of production reflected a complete industrial reinvention achieved in less than 18 months. As output soared, quality assurance became the backbone of success. Every engine faced rigorous trials in purpose-built test cells replicating combat heat and strain. Each ran at full throttle for 4 hours while technicians tracked oil pressure, cylinder temperature, and vibration. Engines that faltered were torn down and studied piece by piece, ensuring no flaw reached the battlefield. The first battlefield proof came at El Alamein in October 1942. British 8th Army Sherman tanks met Rommel's Afrika Korps, whose panzers were powered by finely crafted Maybach engines. British crews, long plagued by breakdowns, were astonished by the Sherman's endurance. German tanks required repair after 50-mile drives. Shermans, powered by Continental's adapted aircraft engines, maintained 25-mile-per-hour speeds across 200 miles of desert without a single major failure. The key difference was philosophy. German design chased mechanical perfection through precision machining, while American engineering favored rugged durability and sustained operation. Lieutenant Robert Hayes of Britain's 7th Armored Division noted in his after-action report that his squadron of 16 Shermans kept 15 operational over a 7-day, 200-mile advance, an availability rate unheard of in armored warfare. In contrast, German units lost up to 40% of their tanks to breakdowns over similar distances. This reliability marked a strategic shift. In Tunisia in spring 1943, American crews found that our 975 engines ran 200 hours between overhauls, 50 more than their German counterparts. That modest difference translated into overwhelming battlefield presence. Sergeant First Class Michael Rodriguez of the 1st Armored Division wrote home, "The Shermans don't quit when you need them most." His tank covered 300 miles without a single failure. German crews, despite driving technically superior machines, could not match this dependability. The impact became unmistakable during the invasion of Sicily in July 1943. Sherman tanks, powered by Continental's radials, advanced 18 hours a day through rugged terrain, denying German defenders a time to regroup or fortify positions. By mid-year, Continental employed 18,000 workers and produced engines at an average cost of $8,500, nearly a third less than Germany's custom-built tank engines. That cost edge fueled mass production for U.S., British, Soviet, and Free French forces under Lend-Lease. German intelligence began to acknowledge what their generals already sensed. Reports estimated that American tank engine outputs surpassed total German tank manufacturing by more than 2-to-1, a ratio that spelled strategic collapse. What had started as an improvised adaptation of an aircraft engine had evolved into a decisive advantage of industrial philosophy over mechanical purism. By the middle of 1943, Continental Motors had achieved what no other factory in history had done, producing more tank engines each month than Germany built tanks in an entire year. The stage was set for Normandy, where the ultimate question would be answered. Could American ingenuity and mass production overcome German precision and perfection on the world's most decisive battlefield? Complete tanks rolled off the lines in numbers that shattered every pre-war assumption about American industrial limits. Continental's Detroit plant turned out 2,500 R975 engines per month, employing 18,000 workers on non-stop three-shift rotations. Each engine cost just $8,500 to produce, far below the $12,000 price tag of custom-built German tank engines. That cost advantage enabled a scale of mass production the Axis could scarcely imagine. But the achievement wasn't only in quantity, it came through relentless refinement. Continental engineers introduced 17 key improvements to the original R975 design, each born from battlefield feedback from North Africa, Sicily, and the Pacific. Strengthened crankshafts raised torque from 1,800 to 2,040 foot-pounds. Carburetor redesigns improved fuel efficiency by 10%. Service life extended from 166 to over 200 hours between overhauls, a mechanical evolution guided by war itself. Yet mass production brought new complications that threatened to undo the progress. By mid-1943, field reports revealed premature failures averaging just 166 operating hours, far below expectations. Tank crews complained that dust filters clogged within days in desert conditions, suffocating engines during combat. Maintenance demand soared to 132 man-hours per tank per month, pushing supply chains to their breaking point. Quality Supervisor Margaret Chen traced the root cause through meticulous inspection of returned engines. Under pressure to meet quotas, Continental had turned to dozens of subcontractors unfamiliar with aircraft-grade precision. Cylinder bores varied by thousandths of an inch across suppliers. Piston rings built to automotive standards collapsed under the intense pressures of radial combustion. Oil filters meant for cars failed to stop fine desert sand. Continental's counterattack on these problems became a model of wartime ingenuity. Chief Engineer Robert McNamara led the creation of the R975C4, a refined engine embodying every lesson learned from 18 months of battle. Power output jumped from 432 to 493 horsepower through a redesigned cylinder head, while torque climbed to 2,400 foot-pounds, giving Sherman tanks acceleration on par with the German Panther despite their greater weight. The C4 introduced a revolutionary multi-stage dust filtration system specifically tailored for desert warfare, preventing sand intrusion without restricting airflow. Its oil circulation system was completely overhauled with larger pumps and finer filtration, extending lubricant life under extreme heat. Most crucially, Continental took full control of its supply chain, enforcing inspection standards equal to those used for aircraft engines. Testing began at Aberdeen Proving Ground in August 1943, where prototype C4 engines endured grueling conditions that no battlefield could match. Engineers subjected them to continuous full-power operation inside artificial dust storms replicating Sahara conditions. Temperature cycling ranged from Arctic cold to blistering desert heat, while vibration rigs delivered forces beyond combat shocks. The results surpassed every prior American benchmark. The C4 ran 220 uninterrupted hours without failure, outperforming even Germany's best Maybach engines. Fuel economy improved to 2.2 miles per gallon, maintaining high-speed capability without overheating. Maintenance intervals stretched to every 150 hours, cutting logistical strain across entire divisions. September 1943 brought the real proof. As the U.S. 1st Armored Division advanced inland from the Italian coast, 200 Sherman tanks powered by R975 C4 engines drove 300 miles through mountainous terrain over 30 straight days. Operational readiness remained above 85% throughout the campaign. German field reports described the Shermans as apparently immune to mechanical failure, a reluctant admission of American engineering triumph. The Italian campaign revealed a deeper strategic truth. German panzers required specialized depots, precision parts, and factory-trained mechanics to stay operational. American Shermans, by contrast, could be repaired in the field by their crews using standard tools and interchangeable components. German tanks stranded in battle had to be hauled back to depots. Shermans were patched up and rolling again within hours. Production data from this period told a broader story. America had transformed the impossible into routine, turning an aircraft engine into the most reliable heartbeat of Allied armor. The results illustrated American industrial dominance in ways that left German strategists deeply alarmed. Continental's monthly production surpassed 2,500 engines while using fewer workers per unit than any comparable German facility. By year's end, total R975 output neared 50,000 engines, more power plants than Germany had built tanks since 1939. The balance of power had shifted decisively, not because of superior engineering in any single component, but because of philosophy. German engines produced more horsepower per pound. Their metallurgy and machining were world-class. But American industry had proven that reliability, simplicity, and volume could defeat perfection when victory depended on endurance. By December 1943, Wehrmacht intelligence concluded that Germany faced an unsolvable equation. U.S. tank production outpaced German capacity nearly 3-1, powered by engines that, though less elegant, ran longer, required less care, and could be built by the thousands. What began as a stopgap adaptation had become a strategic weapon that would shape the war's endgame. June 6, 1944 put the experiment to its ultimate trial. Allied forces stormed the beaches of Normandy with 2,000 Sherman tanks, 1,400 driven by Continental's R975 engines. The stakes were absolute. Failure could prolong the war. Success would vindicate years of improvisation and innovation that had turned aircraft motors into war-winning machines. Waiting behind the Atlantic Wall, German forces deployed their finest creations. Panthers with 700 horsepower Maybachs and Tigers boasting 650 horsepower giants, the apex of mechanical craftsmanship. In one-on-one duels, their superiority was undeniable. German armor and firepower shredded Shermans at range, proving technical excellence still mattered in isolated encounters. Yet as the campaign wore on, logistics, not lethality, decided the outcome. German engines demanded synthetic lubricants, precision servicing, and spare parts from factories already crippled by Allied bombing. Panthers and Tigers broke down as often as they fought. Each required recovery to depots hundreds of miles away. The R975, meanwhile, ran on ordinary gasoline from any Allied dump. Its maintenance could be performed by crews in the field with standard tools and parts shipped from dozens of safe American factories. The math was brutal. German armored divisions averaged barely 30% operational readiness, crippled by shortages and maintenance backlogs. Sherman formations maintained 85% availability throughout continuous fighting. That reliability, combined with overwhelming numbers, tilted every engagement. Allied air supremacy compounded the imbalance. German recovery crews could no longer reach disabled tanks without being attacked. Wrecks littered the fields. American Shermans, by contrast, were retrieved and repaired under full air cover, returning to battle in days. September 1944 brought the decisive clash near Aricourt, France, the largest tank engagement in Western Europe. The 4th Armored Division's Shermans faced the German Panthers head-on. On paper, the odds were hopeless. The Panther's long 75mm gun could pierce a Sherman from over 2,000 yards, but the battlefield told a different story. American tanks entered the fight after months of non-stop operation, their R975 engines still delivering full power. German crews arrived in machines barely broken in, many with fewer than 100 hours of total running time and engines already showing fatigue. The result stunned observers. Despite inferior guns and thinner armor, the Shermans maneuvered faster, outlasted their opponents, and used superior coordination to destroy over 80 Panthers in a single engagement. Continental's engine gamble had come full circle. The aircraft motor that was once dismissed as impossible had become the mechanical heart of Allied victory, proof that mass production and practical design could outfight precision when the world's fate hung in the balance. Suffering from poor maintenance and inferior lubricants, many German tanks failed before firing a shot. The battle raged for 3 days, ending with more than 200 German tanks destroyed or abandoned against just 25 American losses. Yet the true difference lay not in firepower, but in mechanical endurance. Panthers that survived initial clashes often broke down while maneuvering, stranded and exposed to U.S. artillery and tank destroyers. The Shermans, by contrast, stayed mobile throughout, maintaining the tactical agility German commanders could no longer match despite their technological edge. October 1944 delivered Continental's final vindication. General George Patton's Third Army advanced 200 miles in 10 days, an unprecedented tempo of armored warfare. Sherman tanks ran for 18 hours a day at full power, their R975 engine performing flawlessly under relentless demand. German Panthers, restricted by fragile engines, averaged barely 6 hours before failures forced unscheduled halts, collapsing defensive coordination. Ammunition expenditure told the story even more clearly. Sherman crews fired far more rounds per day than German units, not because their guns were better, but because their engines kept them fighting. American crews grew confident in the unshakable dependability of their machines, which emboldened aggressive tactics. German tankers, conversely, grew cautious, their confidence eroded by repeated breakdowns. Wehrmacht after-action reports conceded that mechanical weakness, not enemy fire, was crippling their armored forces. Commanders lamented that American tanks appeared to operate without limits, staying in battle long after German engines had failed. The psychological effect was profound. Fear of mechanical collapse began shaping German battlefield decisions as much as Allied firepower did. By November 1944, Continental Motors had produced more than 50,000 R975 engines, compared to Wright Aeronautical's 7,000 aircraft versions built on the same design. The feat marked a complete metamorphosis of American industrial capability, a proof that adaptation and production scale could outmatch the finest bespoke engineering. The Normandy campaign had already proven that Continental's gamble had succeeded beyond all expectation, but its ultimate proving ground lay ahead, inside Germany itself, where the collapsing Wehrmacht would deploy its most advanced weapons in a final, desperate defense against an enemy whose greatest weapon was not a single tank or gun, but a relentless rhythm of an aircraft engine reborn for war.